Hi, everyone. Thank you so much for coming to my talk today. Um, Today, I decided to talk about something that sits at the intersection of data science, software engineering, and high-performance computing. I decided to do this talk because I think if you understand the system that you're using as a data scientist, it's better to write experiments, it's easier, more efficient, and vice versa. If you're a software engineer, it's way better to design the system when you understand what the user actually wants. Also, in the beginning, I done like high-level slides, but then I thought, oh, it's PyCon, a technical conference. So if you don't know some of the wording, please feel free to catch me after this presentation. We can discuss, talk about it, and dig deeper. Who am I and why this talk? So my name is Jaunė Malūkaitė. I now work as a software engineer at Common AI CIC, which is a company based in Cambridge. I used to work as a data scientist at IBM for almost 2.5 years. And also I did transformer research in the Institute of Data Science based in Vilnius before. Then I moved to Cambridge to study my MPhil in data intensive science, which I finished in October this year. And then I got interested into compute heavy systems, specifically high performance computing and infrastructure. Some additional information about what I do outside of work. So I'm interested in AI fruitfulness and explainability. I'm doing some research in it. And also I'm training for a triathlon. So if at any point during this presentation you feel that it's written by someone who thinks suffering builds character, you might be right. And a good tip for me that works, so if you're stuck in debugging some kind of problem, just have a break, go for a run, eat, rethink, and then it's way easier to solve it. And let's move on to the main presentation, which is mostly on compute. And I would like to start with the question, why is it so difficult to get compute when you actually need it? Well, I had this problem multiple times when I conducted research, mostly transformer research, also when I did data science work at the University of Cambridge. Here you can see their supercomputer, which looks really nice. It has a lot of wires, a lot of GPUs, but we will go deeper in a bit. What I saw was the same pattern that I had all of the experiments ready. I knew what I wanted to do. Just getting compute was so difficult and it took so much time that I would end up submitting the job, then checking the queue, then checking again the queue, then again. And it was so frustrating. It took so much time, so many nerves that I thought, why? What's the point? Then I thought maybe it would be nice to automate this. That's why I joined Common AI Compute. And what we do there is we try to make it easier for users to use compute resources. We do it by authenticating the user, having one control plane for all clouds, including AWS, Lambda, many more on-premises devices. And since this is a bit of a technical talk, we will go deeper into the on-prem side. Also, it's nice to do some monitoring. Because I worked as a data scientist, I believe it's really important, and I will give you some tips about it in a bit. From the user side, at least for me, I would like to have something easy. I would like to launch a cluster, then to check if it's successfully launched. Here we can see that it is. And then check the status, what actually happened, meaning when it was provisioned, what is the uptime, and if everything is okay. Also then to easily delete it, not going to the cloud manually, but just writing the command CI delete and checking that it was actually withdrawn. But then eventually comes the dangerous part. You are using different clouds like AWS, Google Cloud, Lambda Cloud, but then you think maybe you want something that is actually on premises. It sounds difficult and dangerous because you need a lot of money, a big budget for it, but it might starting from something smaller, like NVIDIA DGX Spark. And how does it look like? I made this picture of, at least for me, it looks really nice, this gold color plating on top. And what is nice about it, that it's kind of strong. It has Grace Blackwell architecture, which means that the CPU and GPU is tightly integrated together. Also, one unified system memory, which means that CPU and GPU are sharing the same space. High low precision AI throughput, and also data center style networking. In this case, it's ConnectX-7. I will talk a bit about ConnectX-8, but what maybe you should like to take into account is that it is 200 gigabytes per second. Also, Spark includes software stack, which is ready to use, also has inference workflows, tutorials for easy setup. I tried them myself. They are super easy to use. But what is important, you don't actually know what is happening inside the system. That's where data science perspective comes into account, which means that observability is super important. Before scaling, it is important to understand what the system is doing. What is the temperature? How much memory is being used? How much capacity you still have left? Maybe someone else submitted a job and you want to understand what the system is doing before something crashes. So my tip for tooling would be Prometheus. This is for metric gathering, Grafana for dashboarding, and Loki for gathering failures, errors, and just debugging stuff. I would recommend starting with, from my perspective, a local inference workflow, NVIDIA tutorials to validate the setup, that everything is working, that you have the stack that you need, and also maybe writing a simple bash script to set up everything cleanly, also simply, and just validating that everything works. How this could look like, for instance, start DCGM Explorer, which is NVIDIA's official data explorer. This is a bash script that I wrote, and yeah, it's really simple. You just run the command and everything is set up. But eventually comes a thought that you want virtual machines. They are super beneficial, they are super popular now, but you end up seeing that, for instance, Spark doesn't support it. And you want to try something before actually building a cluster, because clusters are super expensive. You don't want them to break. And then you come across a thought that maybe it's worth building a dummy cluster. Because a powerful machine helps, but some systems problems only show up on scale. This is one key takeaway that I want you to take from this session, and we will dig deeper now. What does that mean? In the beginning, when I joined the company after graduation, I didn't understand most of the terms that are being used. My engineering manager would say, the NIC will go over PCIe. What is a NIC? What is a PCIe? I had no idea. Then my manager would say, Bluefield will help with that. Again, what is Bluefield? Still don't know. IPMI will be useful when things goes wrong. We should think about topology. Storage is going to be complicated. It is still complicated as it was in the beginning. And we should think about RDMA early. My inner thoughts were, I was gaining vocabulary faster than understanding it at first. And I know that many of you might feel this. In the beginning, you're kind of lost, but not really. You still don't have the intuition what's going on, but bit by bit you understand more details, more relationships between technologies, and it becomes way easier to build intuition. And if we talk about topology, let's take, for example, NVIDIA's traditional topology, which has 2 system memories, 2 CPUs, in this case, in this example, PCIe switches, NICs, GPUs, and VMEs. So shortly, a CPU is the brain of the system. It's for the software stack. GPUs, I assume a lot of data scientists are using for AI model training. NICs are for connecting the system to the outer network, because you want the system to connect to other systems. Also, PCIe, this is an internal connection. So imagine like a highway between CPUs, GPUs, NICs, and other details. And the switch is the junction which actually connects all of this. And in VMEs, we will talk about them shortly in more detail in a bit, but they are basically fast storage, because we need fast storage for lots of data, for model training, and for different bits. But what's wrong with this traditional topology? It's that it has many discrete hops. That means that CPUs connect through multiple PCIe switches before reaching GPUs and NICs. They have mixed communication paths, GPU with CPU, GPU with NIC traffic, and also not that simple paths. Also, there's more components to manage. As you can see, separate CPUs, switches, NICs, DPUs, and VMEs. Also, what I want to take into account is that this time it's ConnectX-7 used, and as we can see, NIC has 400 gigabytes per second. But if we change this topology and look to this side, to the PCI switches, and use something like ConnectX-8, which simplifies the topology, we end up having something like this. Now 400 gigabytes per second changed to 800 gigabytes per second. We have fewer discrete components. As you can see, NIC and PCIe is connected. The switch is inside. It's only one thing. It looks cleaner. Also, it has less paths, is more direct, and is a more uniform structure. Besides this, it has higher network bandwidth, as I showed you. Changes from 200 gigabytes per second to 400, and from the NIC it goes to 800. It's also an example from NVIDIA, but we are trying this in practice, actually building this and checking whether it works. And how does it look like? Of course, I took this picture. It's a ConnectX-8. It's very pretty. Again, nice color, a spark. The system looks really nice. And what it actually does, I didn't want to go into too deep into the maths, but I wrote one formula. So imagine, we have a number of GPUs. We have the latency overhead, the message size, the effective bandwidth. And what we want to do is we want to reduce the communication time. But that means that if you use more GPUs, there's more collective communication. And better topology, in this case, ConnectX-8, improves an effective bandwidth and a cleaner GPU to NIC path, which reduces the actual communication costs. It's not actually a universal replacement, and it worked in our case. It might not work for other people, other systems, but it's something worth trying if you have the budget. And overall, I want to conclude that when communication paths are improved with something like ConnectX-8, the part of distributed training that the GPUs wait on is also improved. Now let's move on to networking, which is the next bottleneck. What networking means is that when we scale beyond one GPU or one server, networking becomes part of the compute path, because you want the system to connect to the outer network, you want the system to connect to different parts of the components, but actually training, especially artificial intelligence training, is communication heavy. We have gradients, parameters, checkpoints. We have so much things happening that we want to share between the system components. And the network actually affects the scaling efficiency, because more GPUs do not actually help if they spend on the waiting time of communication, which we saw from the previous formula. That's why topology and networking are linked together. This is a strong relationship between the components. A cleaner topology helps to create predictable GPU to network paths. It helps for developers to understand what is happening, what the failures might be inside, and just to understand what kind of experiments can be conducted in the system. And now let's move on to my least favorite part, which is storage. It's still a super complicated problem because storage is super expensive. There's not a lot of fast storage available in the market right now. You need to wait for quite a lot of time, but you want to use AI systems, especially if you're building a cluster. You want to have something to train your model on. And there is a big problem, because nowadays the data sets are getting bigger and bigger. checkpoints are creating such a huge heavy write traffic, and many GPUs amplify one actual storage layer. So the problem is not only in the capacity, but also in the latency, concurrency, and throughput. And the challenge is delivering the data that you need at speed and when the system needs it. So when you're trying to do an experiment, you want the model actually to get the data fastly and not to be stuck in the system. But performance storage is not cheap, as I said. So what does that mean, not cheap? It means that it's more expensive than gold, actually. So as we can see from this graph, nowadays it's really expensive. This graph is from January 16, 2026. It's now getting higher and higher each day, but that means that a lot of companies are actually using their own storage, their own resources, and they want to use the best possible SSD cards as possible. And from software side, because it's focused on software engineering, right? So let's talk about two open source tools, which are Ceph and Lustre. They are both open source. And what's the difference between them? Ceph, this is a unified storage platform. That means that it uses objects, blocks, file interfaces at the same storage cluster. It's really good for mixed AI platforms. So if you're not doing only super deep research, but you just want to do experiments, try different, just to hypertune, use notebooks, this is a really good software for your storage layer. And also it uses algorithmic data placement called Crush. So it takes into account where to put your actual data to get it super fastly. The other one is Lustre. There's some documentation about it, but it's not that frequently used because it's more high performance computing and more in-depth research. It's a really good choice for sequential training reads. The core optimization point is considered large file input and output. Also, it's best at large shared file throughput, and it uses a parallel POSIX file system. That means that the metadata and the object storage are separate. What it means for data scientists, because it was data science lessons. So I would recommend choosing Lustre when your training is actually dominated by large files, high throughput shared reads, when your main requirement is to keep many GPUs fed from one fast POSIX file system, and choose Ceph if your platform needs to serve multiple storage modes at once, if you want a more flexible storage system, and if you have data sets in S3 bucket. If you plan actually to mostly run large-scale training, I would choose Lustre. A lot of researchers use this kind of software, but if you need a more flexible, once again, data platform, then I would go with Ceph. Now let's move on to one practical systems tool, because I assume it's worth knowing not only the overall hardware stuff, not only the software stuff, but also what is actually happening with your code at runtime and how you can actually optimize it, what kind of memory is used, where is the data placed, and what is happening inside. So the tool is Volgren. Maybe you have heard about it. Me personally, I used with C++ on a supercomputer. It is a dynamic analysis framework for running a program under instrumentation rather than executing it normally. It takes a bit longer, but then you get a really nice output with the errors, with all of the information about memory, cache level, and so on. A few details. So memcheck is used for memory errors, Helgren for threading issues, Colgren for profiling and cache behavior, Massive for heap profiling, and how to use it. So we can start with flags, with debugging flags, for instance -G or -O0, which are kind of safe to use. Then we can run the program with the chosen tool, for example, Volgren memory check, and test the program. And it gives us an output with the error type, address, call stack, and summary. So the key takeaway is that it's not only worth knowing about the GPU, CPU, the topology, the networking. It's worth knowing about all of the relationships and how they fit together. Because as a data scientist, you actually want to increase your creativity when you conduct experiments, but sometimes the system has limitations that you don't understand and you are frustrated what is happening actually inside. That is why I believe that it's really worth knowing what is the actual system doing inside. For software engineers, I believe that it's really nice to know whether the problem is in the code, in the system, or actually something went wrong with the hardware. So the key takeaway, please use observability, know your system that you're using, and always think about the user that is using your system or platform. It's not only the components, it's the relationship and how the whole system fits together. Thank you so much for coming to this talk. If you have any questions, please grab me and we can chat outside. Thanks.